Hello, this is just an auspicious day of our recording of the Cosmology video, which is actually Inflationary Cosmology the 5th or the 6th video, I can't remember very well, but for the sake of those cases, we have to continue more assiduously and elegantly to our discussion towards those models of the universe which describe the expansion or the behavior of the universe, which is corresponding that the cosmological fluids which describes the entire space it's embedded in and it's distributed along. So there are actually two essential and fundamental objects we have to use in our worlds, which are actually the cosmological fluids, the cosmic fluids, let's say, and the other is the geometry of the space, geometry. Which they are, well, both of those contributions and equations in the left hand side and the right hand side are equal and they are consistent. So equivalence is being done, or it's consistent by or with respect to the Einstein's field equations, and we will have to solve it with respect to the tensor algebra. But this is actually the next series issue. Okay, so in this video, well, permit me then to enlighten about what I have done hitherto, and actually specifically the previous video we had closed universe, which is actually the universe starts from the Big Bang due to our assumption which was actually the standard cosmology and the perfect fluid. As in the tensor notation, I can say, or I might be say, if I could, well, if I have presented it to you, well, yeah, that would be nice for me. But I did not present anything about the tensors yet. So if we were talking about the tensors and their notations, the cosmological fluids, which is perfect, is equivalent or corresponding to the covariant derivative of the stress energy tensor is 0. All right, so which is to say it is actually a stationary case. So we are dealing with the spatial components of the metric, and as you can see, we have derived every equation hitherto with respect to the coordinates, and the parameter of ours was the time. So we have actually defined the conformal time, which is actually the time that is required for a light beam to travel from the first source of the universe, which are actually the charts on that early times, from that era to today's universe, the present. So the amount of time that is required for a light beam to travel alongside the universe is actually defined as the conformal time, but this is not actually starting from t equals 0, the Big Bang, as our theory requires. So in the previous video we had the closed geometry of the universe, which is expanding, right? Expanding to some region of space, which we call the maximum radius of the space, and afterwards it collapses back. The reason of the collapse, the reason behind this scenario or the event is due to the gravitational attractions in the universe. They are inevitably affecting each other. If you have a mass and the masses are inside of their scalar potentials, the potential is actually the functions of space, and we define it with respect to the centrifugal barriers, for example, or the centrifugal potential, let's say. And the most important feature of those potentials are that they can be represented with the radial functions, not angular, nor neither angular parts nor the time evolutionary parts, because it is actually the reason why we call them centrifugal potentials. All right, they are corresponding to the spherical distribution of the potential, which produced by the presence of the source inside of it. So it's actually Gauss divergence theorem, right? You can indicate, you can deduce easily from my implying, right? So those centrifugal barriers or the potentials, for the sake of the cases to be easy, that we have discussed them for the first time as stationary fields, which were produced by the presence of the gravitational material inside of these spheres, right? So those gravitational materials were actually the galaxies. So we actually studied the long scale, the big scale uniformity of the universe. So what we have seen, due to the expansion of the universe, which is corresponding that the space-time is stretching as the space or the universe expands, as the universe expands, sorry for my grammar, as it stretches out, the material inside of this geometry, which we call this cosmic fluid, is also stretching too. So the expansion does work on the gravitational material or whatever inside of this universe, whatever the universe is filled with. All right, so the question is how we defined the equations, right? It was actually our elucidation was actually describing the stationary gravitational fields, which are actually conservative fields. So the source which produces the gravitational field around it was stable, but due to the expansion, due to the kinetical energy which is coming from the Big Bang, and we have called this the kinetic energy of the field, because this is a balloon, you can imagine it, and it was expanded to the future. This expansion was increasing in the present universe, but we have seen that this expansion also causes to those gravitational fields and the mass distributions around in the universe to be non-stable. And afterwards, we have seen that the gravitational field is also evolving by time, which is the reason why the sources that they produce the field are moving inside. They are interacting, all right. Well, they tend to come closer due to the gravitational attractions, the distances between them. What we have expected should be getting closer and closer. Well, it was actually until 1998, the observation, you know that. But the expectations were not consistent with the observational data on that very times, which were captured and which were miraculously, well, the consequences and the data was miraculous on that very times. They have different contributions in the expansion of the universe, and the most important one was the prediction of the cosmological constants. It was actually the first time the theory was not true at all. Because due to the gravitational attractions, and as we saw in the previous video, the universe should be collapsed back after some region, after some time, right? We have find that it was actually the oscillatory universe due to the harmonic functions, cosine and sine functions, for the time that is required for the universe to grow and collapse back, and also as this parameter time passes, elapses, you have some change and interchangeable displacements inside of the universe, what we call scale factors. And we explain the scale factor with respect to the cosmological fluid density. It was actually a non-relativistic matter. Alright, in this video, I talk a lot, sorry for that. In this video, we intend to do the same thing for the open geometry of the universe, which is corresponding that infinitely expansion of the universe is right now occurring. And what we have to find, and what we are expecting to find, that some functions, alright, of course, we have to find out some functions, but which are diverge as the time goes infinity, or you don't need the time to go to the infinity. It can be dark energy and other densities, which is actually pulls up and push the universe inevitably and so expeditiously, so rapidly that the expansion is accelerating faster and faster. So again, your theory is just gone. It's all in vain to explain that without the contributions of the pressure on the space-time. So, as you can imagine, that we were doing with standard cosmology model, which does not include the pressure terms of the cosmological fluids, right? And we have three essential models, which are correspond to the geometry of the space. It can be flat, closed, or open geometry. And now today is the issue of the open geometry of the universe. Expansion will be determined by the geometry and the density of fluid. In the next videos, afterwards the cosmology representations, I intend to continue with the tensor algebra, not explain the topological spaces, topological spaces and manifolds, but we will directly focus on the tensor notation and the solutions of the field equations with respect to these cosmological models or black holes, whatever else, compact sources, spherical compact sources. For example, you have a star. You can model the physics inside of the star with respect to the Schwarzschild metric, and you have to solve it with respect to the vacuum solution of this metric, because the star's radius reaches some maximum distance from the core, and afterwards there is nothing for the theory, which is called the vacuum solutions. So you are interested in the solutions and the fields that were produced and that were embedded into this geometry, which is called spherical geometry. And this is why, this is the reason why we are studying the Schwarzschild metric. It is not rotating. If it were, for example, it will be called or said to be Kerr-Newman metric. Well, you can add the contribution of the electric charge and the magnetic forces, then your black hole becomes non-strong black hole, if I pronounce it truly. All right, now let's get started. All right. Oh, sorry, I have to mention one more thing too. I'm losing good then. I had some alcohol a little bit inside of it. That's fine. Yeah. Okay. I forgot what to say. Oh, yeah, well, okay. We have to define other parameters which will explain the nature better than the notation of ours. The notation I have preferred to continue with was the notation of MIT's lectures of Ellen Harvey Guth and the Leonard Suskind's lecture notes from the Standford University. Their notes and lecture presentations were mixed in my videos, so I have actually added some more terms to explain it more intuitively and clearly for you, but we're gonna do this right now. Alright, we will keep going with the video. I'm sorry I have to record this vertically. My tripod of my telescope allows me to do it. Otherwise, I have no chance to record that horizontally. All right, this is what we have to do right now. Sorry for now. When I get back to home, actually I am home to Antalya, where the university lies. I will have the better view or aspects of chalkboard. Okay. Alright, so if you can remember that we have the Hubble function, right? A dot over A with respect to time, and the reason we can solve with respect to the spatial components is due to our assumption we are studying in the standard model cosmology with the perfect fluid. So you can solve it with respect, well, it says that there lies or there exists a killing vector that the metric on time and its covariant derivative is not changing. So it's constant. The derivation of metric with respect to the zero component of the metric is not varying. It's constant and conservative, and it is due to that the covariant derivative of the stress energy tensor, let's say, is 0. or you can express it. Well, this is actually the conservation law, all right, which is to say that nu, the alpha beta. Well, it's a second order mixed tensor. You can better put it down, lower the indice with respect to the contraction of the metric tensor. I just write it down like that. It can be written as the other forms. It doesn't problem that much. So it's the minus the Christoffel symbols. So nu beta. So we have the other parameter. Let's say gamma. And we have T gamma alpha. Okay. Dx mu and whatever lies behind that. I'm just listening to the cats outside. They are fighting. Yeah, is actually the covariant and the contravariant form here is that the gamma mu. It's better to say alpha must be here, gamma must be here, beta, and we have gamma dx mu. Well, this is actually 0, corresponding to the presence of the Killings vector and the Lie identity. Okay, this is just the covariant derivative of the stress energy tensor here. It's well, the zeroth component must be conservative, all right? So which is to say T naught naught. Well, for this notation, this is that one. Well, it's better for us to use this one, the alpha beta. Imagine if you were prefer to do this with respect to the two lower indices, then it will be equal that this might be the minus sign, and the indices must be there are no indices on the upper indices that are contravariant indices. Okay, with respect to beta and alpha. So the reason we can write it down easily is is due to that the T naught naught, the time component, is conservative. Okay, the time derivations is 0, which is corresponding that the density is stable on this given region space-time. So okay, let's turn back to our calculation. Well, so as to define the decretion parameter, which is indicating that the universe and the rates of the slowing down of the universe due to the gravitational attractions or anything which is or which has the contribution opposed to the acceleration in the future, towards the future, forwardly. The reason what we are explaining this with respect to the Hubble parameter or the function, it's because the Hubble parameter itself is including the density and the geometry inside, as we derived in the previous cases of ours. Are we recording, by the way? And we are. Okay. So as to define this constant, I'm just taking the first time derivative of this function h dot, and which is a double dot of t divided by a of t minus the second one minus a dot divided by a squared of t, and the derivation of it with respect to the t is a dot squared, right? As can be seen, this is h squared here, which we can continue as h squared of t. So in terms of or let's say with respect to the intention of ours to write this equation in terms of Hubble parameter h, I multiply and divide both sides in this equation in this ratio with respect to the h squared, okay? So h dot becomes h dot h squared a double dot of t. Well, h is also the functions of time, okay? A of t, h squared, and minus h squared of t. Well, let's say that here. So h squared a double dot divided by, well, this is just a notation, okay? But it will be helpful in our afterwards videos, the next videos, okay? H squared of t. Well, I'm not writing down the functions dependencies, but you should remember or don't forget that they are the functions of time, okay? Minus 1. So I will, well, I call this, I intend to call this term is actually the degradation parameter. Let's check if we are wrong. Oh, in my notations, I defined here, or sorry, I multiplied here with the negative h. So we can continue the same thing here, which can be expressed as h, so minus multiplied by the minus h squared, all right? So you have here this thing and here this thing, all right? Sorry. Yeah. So our equation becomes the same thing again. Well, it will not change anything, but I need to, well, I would like to keep up with the other presentations and notations of the other varied miscellaneous books and the other lecturers. I don't know, I'm not a lecturer, just representing that. Minus h squared 1 minus a double dot divided by h squared of a. So I call that minus h squared 1 plus q. So the q is smaller than 0. Q, let's say, minus a double dot divided by h squared of a is closer, smaller than the 0. It's less than 0, let's say. So if we turn back to our definition of Friedmann equations with respect to the previous videos, the first order Friedmann equation was a dot over a squared equals 8 pi g rho of t. Well, those are actually the time dependent, right? In minus kc squared divided by a squared of t. In my calculations, I will take the speed of light as 1, and we will study the open universe corresponding at the positive negative curvatures. So it's actually the minus 1. This is 1, so this will be entire function will be the plus 1 in the right hand side, and we're gonna solve this today. So writing down again with respect to the parametrization of R's, this notation, I can continue as with respect to the HR. Okay, the same procedure occurs here. A dot. Oops, we have the other problem here. We have second order. Yeah, it's better to use the second order Friedmann equation, and afterwards we will change our definitions and variables to the first order Friedmann equation. Why? Because I forgot that, well, just check. We have the first time derivative here, first order derivation, but in here we have second order. We can't do this in here. Maybe you have guessed that I intended to multiply both sides by minus h squared and a of t here, but here is not a double dot, here is a dot. I can't do this. I need to write down the second order equation and write it down with respect to our changing of variables in here, parameterization. So the second order Friedmann equation was minus 4 pi g rho of t divided by 3 a of t. Well, I can take here a of t. So multiply both sides as we did in here with respect to the minus h squared a double dot divided by minus h squared a of t. And this is actually the functions of time, don't forget. And here we have minus 4 pi g rho of t divided by 3. And this is actually our parameter. Where is that? Here is this, the degradation parameter q as a function of time. So it becomes minus q h squared, both the functions of time. I am not writing down, all right? Equals 4 pi g rho divided by 3. If not visible from that place, I can write it down here. Q h squared 4 pi g rho divided by 3. So if you know the density, and if you know this parameter, and if you know this parameter, you also know the Hubble expansion rate, then you can find out the, well, any of them. If you know both, because those 4 pi g divided by 3 is the constant number. It doesn't play a role in this equation, so the expansion is linear, as can be seen with respect to the density, but is a function. For the matter-dominated case, it becomes 1 over a cube, the inverse law of the inverse the third, right? And it's for radiation the a to the 4, 1 over a to the 4. Okay, I'm going to use that in our notations. Now I would like to imagine from the first order Friedmann equation, and it was, let's say, h squared of t equals 8 pi g rho divided by 3 as a function of time minus kc squared divided by a squared of t, right? So let's take it here to the left hand side. Here is minus, here is equal and minus, right? Well, I'm going to replace it with respect to this function. So I'm going to take that. And the same results is actually happening again. All right. Now we take. Well, I did the same thing actually in the cosmology, the Turkish video actually. What was that? 3.6 or 5. Some of them. The same parameterization. It doesn't change the results. So is it visible here? I'm going to. Oh, very nice, very nice. It's visible. Very nice. Now we can clean here. We will continue to write down the equations again. Okay. Well, you can remember that we have this relation here, so I can solve it with respect to the rho, the density, and which is equal 3q h squared divided by 4 pi g, right? Is it clear? All right. And replace it in this equation, the first order Friedmann equation, okay? Which is to say h squared of t minus 8 pi g divided by 3, and rho of t is here. Both of them are the functions of time. 3qh squared of t. Q is also the function of time. Well, it depends actually. If we are solving for the flat case, flat universe, this is equal to the 1 over half. Or for example, positive or negative curved universe, it's corresponding that the Q must be greater than 1 over half or the less than 1 over half, all right? We have these assumptions. These assumptions are due to the geometry that the fluid itself is restricted and constrained to move and to be in. So the field, which is actually the cosmic fluid, fills the entire space around it. So the space, well, it's not a stationary. The geometry varies with time because due to the expansion, there are deformations. The density of the fluid, the cosmic fluid, is also changing. And we are trying to understand it with respect to the standard cosmology model, all right? 3qh 4 pi 0. Well, minus, so this is minus kc squared divided by a squared of t. So k here is actually the Ricci scalar, right? The curvature scalar, which is coming from the contraction of the Riemann curvature Riemann tensor, and the Riemann tensor is coming from the curvature tensor itself, which is including the derivatives of the Christoffel symbols with respect to the coordinate basis, and the two other multiplication of the Christoffel symbols. All right. Okay. Now we can continue. This guys is vanishing here. So those are two. I'm writing them again. Solution becomes h squared of t minus qh yeah 2qh squared equals minus kc squared divided by a squared of t. So I need to solve for the curvature scalar, which is actually 1, minus 1, or 0 in our models. Let's say minus h squared. I don't want to write it down with minus sign here. H squared 1 minus 2q equal, let's multiply both sides with a squared and divide by c squared. A squared of t divided by c squared equals k. So minus, I take minus k. Here's the minus k for us. So what we know that only this thing, all right, we are interested in. So permit me then to explain that. Okay, so h cannot be 0, and same holds for the scale factor a of t cannot be 0. So the only thing that can be 0 in here is the q. If you are solving for flat case, for k equals 0, the q must be, the right hand side is 0, so the q must be 1 over, so q equals 1 over half, right? For the flat universe, it corresponds that. And for the other models, which is corresponding that the k equals minus 1 or plus 1, we have the values of q as follows. For example, did I write it down in here or not? I didn't. Well, I think I have this in the other page, so I can check it here. Um, Okay, I got the paper here. For flat case, Q equals 1 over half in here. Closed case for Q equals 1, which is actually the previous video's issue. For closed case, Q is greater than 1 over half, and for the open geometry, minus 1, Q is smaller than 1 over half. And well, it's a reminder here, the density of the cosmic fluid for the universe to be flat is about 10 to the 29 grams divided by centimeters cube, which is actually equal. Oh, sorry. Well, that will be an amazing one. So it's not true, but it was actually during the Big Bang and before. Well, I will explain that afterwards, just wait. This is actually the cosmological constant here. This is actually the required density, the magnitude of density for universe to be flat, flat potentialized universe. But we know that the universe is not flat, it's non-flat potentialized universe due to the contributions and due to anisotropy of the space, inhomogeneities of the space. So there are, well, the universe expands all directions, all right, but not with the same rate, depending on the model you are solving. For our model, the universe expands in every direction with the same rate due to the distribution of matter. It is a uniformly distributed universe, which the matter is stable, locally changing, globally not changing, so it's conserved. The total energy and total charge of the universe is conserved, and we are solving for the cosmic fluid to be perfect, which is not changing with time, varying with time, and the distribution of the cosmic fluid, or the density, it's better to say density, is uniformly distributed. Uniform distribution means you have everywhere the same entropy distribution and the same temperature scales. Why the temperature? Well, it takes an important role in the applied physics and the observational cosmology, because the temperature distribution depends on the entropy, and entropy depends on the particles, actually the fields. The presence of any field in a given manifold or given the topological space, you have fluctuations there. All right, so those fluctuations are produced or caused by the presence of the material density. How we know that? Because those are the solutions of the field equations. The left-hand side corresponds or implies the geometry of space, and the right-hand side is the source. Source behaves in the space. For example, if you can imagine with respect to the Hamiltonian dynamics we did in the previous lectures, in the previous discussions of ours, that the Hamiltonian dynamics is valid only for there are constraints, all right, but those constraints are including that the variation of action is 0. So it corresponds that if you have some field or particle, doesn't matter, the kinetical energy and the potential energy of this system must be minimally potentialized, and the system must keep up in the way that is the minimally potentialized, which is called geodesics. In a given time interval, the integral of the kinetical and the potential energy must be minimized, and it must be, well, the variation must be 0. Thus, you can solve it with respect to the Euler-Lagrange equations. If you have constraints, the right-hand side is not 0. But this assumption is valid if you have the source. Of course, you have the source, but the source is not varying globally, but there are local chains. You can check that with respect to the Poisson brackets. The local chains of a system is equal to the global chains. So the partial derivative, well, if the system, for example, the energy, is not the functions of time intuitively, then you can integrate the system. Integrate because the system is invariant under the displacements of time, the time variations, all right? The system is still the same, the energy conserves globally. And the other assumption was the rotational symmetry. The rotational symmetry, we have assumed that our potential field, which was actually centrifugal potential produced by the gravitational masses, was isotropic, which is to say invariant of rotations of space. So every direction, the field distribution is same. So you explain the behavior of these particles which are bounded into this gravitational field, spherical symmetric gravitational field, centrifugal field, radially. So you solve with respect to the inverse squared law, and you explain the dynamics or the trajectory of the objects with respect to the radial solution. So you just draw the vector lines towards the system, towards the object, from the center of mass or the source. It's better to say source, because the source is the reason why that the presence of the gravitational field along the space is produced. So as to understand the strength or the magnitude of the field affecting or attraction affecting on the objects around it, we just measure that with respect to the presence of the test particles. But for the curved manifolds, we have other problems such that the vectors cannot remain the same vectors, and the problem is due to the parallel transport of these vectors. In the curved manifolds, there lies the chains, interchangeable and inevitable chains, as you move the vector from some stationary initial point to the other point on space. So this contribution of chains in the vector represents any field, the vector field, particles, trajectory, doesn't matter. The change from here to here, as you displace it, is coming from the components that were changed as you move along, and the vector itself changed due to the symmetry of the manifold that is embedded and defined in. So it's not easy to do the same gravitational fields in the curved spacetimes. In the curved spacetimes, you need some other quantities, such that some quantities that are invariant with respect to the coordinate frame, and well, even you have those things, the fields are changing. So the variation of the field or the action integral probably will not zero. So you have problems there. For example, you have to perturb the metric. All right, those are actually the problems. And not good problems, actually. We have these things right now, and I'm going to continue with the the matter-dominated open universe. Expansion is infinite. We will see that. We will have hyperbolic functions, and they will diverge. Well, what I was talking about was that we have action, all right? The action integral. There is some parameter here, minus m. So we have this integral is taken along the four-dimensional space-time, the Riemann geometry, or for example, for the easy cases, it becomes Minkowski space, 3 space and 1 time component, let's say for d4x. So you have a given Lagrangian, and the Lagrangian is function of the field, well, it can be a field, so this is actually the position of the scalar field along the space and its derivatives. And this is actually the covariant derivative of a field. Well, the covariant derivative of the scalar is the same as the partial derivative as we are doing in the Euclid's geometry, but if it were a vector field, then it's not true at all, because vector field can be expressed as tensors. For example, the electric and, well, what was the name of it? The Lorentz gauge potential, for example, is a vector field, or maybe, for example, electromagnetic force field is also the other one. Del mu a mu minus del mu a mu. Alright? And the parameter, let's say, for example, prober time. Alright? So if you take the variation of it, it cannot be 0 in the curved manifolds. You have to add contributions on the action. But you have still the same quantities that remain the same, such that the speed of light, well, this is the theory's the fundamental assumption, and the other is that the tensors that are changing with respect to these coordinate transformations. Alright? We will discuss it. I have to take a break. Okay, we continue our notation right now. And we are now solving the open universe, which is negatively curved space-time. We are just solving with respect to the spatial components, and we will keep going. All right, here we begin. Recollect that the first order Friedmann equation, and it's squared 8 pi g divided by 3 rho of t. We are solving for non-relativistic matter. Rho m naught divided by a cube of t. We derived this definition and where it is coming from. Minus kc squared divided by a squared of t. We are solving for open universe, corresponding that the richest scalar is -1, and let speed of light 1. Why? I don't want to see that in our equations. If we don't want to see, well, okay, let's see. Did I take it in my notes? Let's see from here. I didn't. Okay, no need. So if k is -1, this comes plus, and let us multiply every side of this equation with a squared. So we have a dot squared equals 8 pi g rho m naught divided by 3 1 over a of t plus 1, right? And it is equal, a dot is equal the square root of this thing, and which is dA over dt with respect to the time, right? Okay, so dA of t divided by this here is entirely a constant. I call this constant alpha, if I don't remember wrong. Okay. Before we continue, let me introduce our constant here. The same procedure holds as we did in the previous videos for closed universe. I call here alpha the constant 4 pi g rho m naught divided by 3. Alright? I could choose this constant to be 8 pi g rho m divided by 3. But if we do that, when I write the integral in the denominator part, you are not able to write this thing with respect to the parametric solution, or the summation of the square of the summation of two numbers or functions, a plus b squared, for example. All right. If we can't write it down in this formula, then we cannot solve it easily. We prefer this constant to be as defined above in here because of this clearness and precise meaning. All right. So we have dA divided by 2 alpha divided by a of t plus 1 to the square root equals dt. This is the functions of time. All right. I integrate it. Before we integrate it, let's consider this part a little bit more. 2 alpha, I intend to multiply both sides, a and a alpha of t divided by a squared of t, take this part, plus a squared of t divided by a squared of t, and its square root. So, which is equal 1 over a squared of t, 2 alpha a of t plus a squared of t, and its root. So, it's 1 over a out, so dt equals, I will introduce conformal time a minute afterwards, a of t dA of t divided by 2 alpha a of t plus a squared of t square root. Okay, this is my integral right now. I'm going to find it out. Okay. We will define conformal time, which will be better notation. But first, permit me then to solve it with the same notation as we did in the previous videos. ADA divided by, okay, let's open this thing. What is this? Alpha squared plus, alpha squared plus alpha squared, a squared, 2 alpha a, so we need minus alpha squared here, right? Is it correct? Alpha squared vanish, 2 alpha a and a squared. Okay, it's correct now. Here is the 1 over half. All right. So as to find out the solution, I'm going to change the variables. Here is what I say. U of a. Yeah. So U of a equals alpha plus a. Okay. So the differential of it with respect to a is dA, right? Is there anything we need more? Oh yeah, a itself is U of a minus alpha. With these definitions, the integral reads as follows. U of a minus alpha, the dA equals du of a. Okay, let's not write them right now, but remember and never forget that u is the functions of a, all right? Independently. Precisely, it's the functions of a. u minus alpha du divided by, here is the entire thing, u minus, u squared minus alpha squared to the half. Oh, inverse. Not inverse, square root. Alright, here is our integral as follows. So I can distribute it. U du divided by u squared minus alpha squared to the half. Minus alpha was a constant and defined this here. Du divided by u squared minus alpha squared square root, and which is equal to the t. Well, t naught to some t final. We are studying in the standard cosmology, so t naught equals 0 is corresponding to the Big Bang, where the scale factor itself is also 0. This is actually the requirement and the requisition of this inevitable and compulsory requisition of this theory, that the Big Bang is a singularity, which everything is starting to grow up like an explosion. Yeah, it's of course explosion. And in this theory we have the expansion where the expansion is uniform and isotropic, expands in every direction with the same rate due to our assumption, which was the cosmic fluid to be perfect and the space to be open. All right. So we're gonna solve these things. Well, let us continue with undefined integrals. Afterward, we will define them as usually. Okay, what I did use as a changing of variables is quite visible. Well, both of them are visible. I just intend to keep up my own notation. I want to follow my notation. Gamma, I said in that place. Here's gamma. Yeah, gamma u. So gamma u equals u squared, and which is gamma is the functions of u and u is the functions of a. Okay, do not forget that. Minus alpha squared, so the gamma equals 2u du. It's easy now. So, and for here we have a parametric solution here, and where I use that the hyperbolic cosine function. It's getting much more easier. Otherwise, you can solve it if you want with respect to the inverse trigonometric functions and hyperbolic, by the way. If you know, well, of course, if you are good at the derivation of these functions, then you know the result is. Or you can take a parameter for this variable u to be a function, harmonic function, but hyperbolic cosine or sine function. You can try both of them and find out which is better to solve this equation. I choose u of x here, and the parameter is actually gamma, I think. Yeah, gamma. Okay, u gamma equals alpha cos hyperbolic gamma in that place. Am I clear right now in that place? Yeah. Okay, I will find out that the du is alpha sine hyperbolic gamma d
gamma. All right. So I'm writing down the entire thing again. T, well, let's say dt for now. dt. Because I intend to introduce conformal time, and equations will be much more easier and clear afterwards. Here u du, okay, what about that? Okay, 1/2 u du is d gamma divided by u squared minus alpha squared is gamma, and gamma to oh yeah, gamma to the half, 1/2. Okay, minus alpha. In here, du was alpha sine hyperbolic gamma d gamma divided by u squared minus alpha squared, u squared alpha squared cos squared gamma minus alpha squared to the square root. I think I'm getting tired, but it's okay. We are correct now. Okay. Well, I'm thinking that should I define the conformal time right now or 5 minutes later? I don't know, because well, the solution is clear right now. But well, okay. Reminder. Let's say reminder. D eta equals dt over a. We are going to use that. Okay. I will do that 5 minutes later. I'm going to find out the integral here. So here the result is dt equals, well, it doesn't matter. We can multiply dt by 1/a and so forth. D eta. It's easy because we are finding out dt right now. But it's better to use this notation without changing of variables, alright? So this is afterwards. This is the propose, which will be occur afterwards. Which will occur afterwards. Yeah. Plus some constant, let's say c prime. Here minus alpha. Okay, let it stay there. Alpha since hyperbolic gamma d gamma divided by. So in the parentheses, it's actually alpha cos hyperbolic gamma minus 1 to the square root. These things will be gone. We have gamma to the 1/2 plus c prime minus alpha sine hyperbolic gamma d gamma divided by. Here we can use this identity for hyperbolic function. So this is actually sin, right? Sin hyperbolic squared h. Squared minus sin h squared equals 1. So it can be seen that if you take it right left hand side, here is sine hyperbolic gamma. Afterwards you apply this square root. So our integral becomes gamma to the half. I will sum the constants, both of this integral, to the other constants. Let's say entirely c. Oh, sorry, minus here. Alright, so what was the gamma? Gamma in here was u squared minus alpha squared to the half. Somebody speaking aloud. Incorrigible people of my country. I hope their sounds are not detectable from you. Alright, u squared minus alpha squared to the square root minus alpha times the gamma. Well, it's better to define gamma here because this gamma is not the same gamma as in here. Well, this is actually what we can find out from this relation, that u gamma divided by gamma, alpha equals cosh hyperbolic gamma, gamma. So gamma here is actually O, or cos hyperbolic u divided by alpha, right? We can replace it with respect to this function there. Alpha times cosh hyperbolic inverse, of course, u divided by alpha. Alpha is same everywhere because it's a constant number there. Okay. This is a solution, of course, but with application of after we apply the conformal time, it will be more precise and clear for us. Are we recording there right now? Cool. All right. All right. But recall it. U was. What the heck is going on there? I hope there's a monster living in our house. I'm sorry. I think it was my mom. I don't know what really happens there. I think they're alive. Sorry for that. Alright. U here was this thing. Right? Is it the same? Yeah, okay. So gamma equals, well, there's no place left here. I will prefer to continue from here, but please do not forget this integral. It's our main integral, alright? Alright. dt, well, actually it's just t afterwards because we solved the integral. U squared minus alpha squared. U here was alpha plus a squared minus alpha squared to the square root minus alpha cosine hyperbolic, the inverse. U is alpha plus a divided by alpha, which is better to use like a over alpha plus 1. And alpha was, don't forget, 4 pi g rho m naught divided by 3. Alright? Alright, well, as can be seen here, the function, well, this is the time required for the open universe to evolve, but we will focus on here. Why? Because for the large scales, well, not large, but you can. Alright, sorry, these notifications prevent the recording, its continuity is distracted and avoided by those notifications. Well, I lost 20 minutes. I spoke alone. It was not recording as I was speaking. So it's gone to trace, to the waste. Oh, patience, right? Alright, let us define the conformal time again. D eta dt divided by A. Right? And what we have found in the very beginning of our video, that dt was the integral a dA divided by 2 alpha a plus a squared to the square root. If you multiply with respect to the 1 over a, the inverse a, so as to find out the conformal time given in here, we have dA divided by 2 alpha a plus a squared to the square root. They will vanish. Cool. And the solution is, for conformal time eta, cosine hyperbolic a over alpha. Okay, with the same definitions above, which is different from initial time, the present time. This is the conformal time is actually a light beam. The amount of time that is required for a light beam that was produced from the first initial charge of the early times of the universe to travel from that times to present. Okay. So for this electromagnetic wave to come from that times, the early times, this time and the amount of length is corresponding to the age of the universe and radius of the universe. That is the reason why I use in my rows along. It's coming from that. So, well, this is not coming, these light beams are not coming from the Big Bang. Alright, because there are no charts for our assumption. The universe started from the singularity, t equals 0, the Big Bang. But most of those light beams we are using to define the conformal time are coming from the radiation-dominated era, and it's a little bit earlier times. For example, we define for flat case that the radiation-dominated era was about 70,000 years, plus or minus 10,000 from the Big Bang, t equals 0. But we also saw that the curvatures are not important in the early times of the universe, because the universe in the early times was uniform, flatly potentialized, alright, and not uniformly. This is the reason why we see today that black holes and the galaxy clusters are gratified and densified in some regions of space rather or compared to the other space regions. That's why there are massive or supermassive black holes which are so old and coming from the early times of the universe. Alright, so I'm going to find out the A here. A here. There's one thing wrong in here. Yeah. I need some term here like +1, because we did changing of variables. It was like that. Yeah. Okay. Sorry. So A, well, A over alpha +1 equals cos hyperbolic eta. Thus A equals alpha cosine hyperbolic eta -1. This is a scale factor with respect to the conformal time as a function of conformal time. Now, with this knowledge, we can find A d eta equals dt. This is a connection, okay, with the early times to the present time. Alpha cosine hyperbolic eta minus 1 d eta. So t as a function of eta, conformal time, equals alpha sine hyperbolic eta minus eta. That's our definition right now. This has the following graph. Well, with some initial values you can take here as a 1, but important is in here. Oh, sorry. I have forgotten to write down the constant sine hyperbolic eta minus eta. If you were not take the speed of light to be 1, here there must be c squared, okay? And for initial scale factor, if you didn't take it 1, there must be some a naught cube here. It's a constant also, and which is the true notation actually. Okay, but for our notation in the previous videos and the others, it's better for us. So the graph is like this, and for radiation limited case, it becomes, well, scale factor becomes the sine hyperbolic instead of cosine, and t that is required is become the cosine hyperbolic, as can be indicated. For closed geometry, we have found that it was actually collapsing back after some critical time and critical density in here. All right, this is actually the evolution of the open universe. I'm tired. In the next video, we are going to do the thermodynamics of the universe with respect to the first law. So there's a work which is being done on the finite region of the space-time, which the space-time region is filled with the energy densities. So as the universe expands, it does work on the finite region, finite volume that we have, that we will choose on the next video. So this work will change and fluctuate the material density in this imaginary surface of the box. So the pressure will be changed, and due to the change of the pressure, the volume will be changed. So there's a thermodynamic work in that place. We are going to apply the first law of thermodynamics towards the expansion of the universe with respect to the different kind of material densities, and we will find out the parameters of state parameters and equations of state with respect to the different kind of cosmic fluids, not only two of them, radiation or matter-dominated cases. Thank you.